Okay, this video covers section 2.3, and the title of the section is Volumes of Revolution, Cylindrical Shells, and it's very similar to the last section we covered, where we took regions and rotated them about an axis to find a volume. But in the last section, we looked at two specific methods. We looked at the disk method and the washer method. In this section, we explore a new method where we look at cylinders, and so it's called the method of cylindrical shells. The reason why we kind of talk about this new method is it gives us some flexibility as far as the axis which we rotate about. So if you remember from the last section, if we had a region that was rotating about the x-axis, our representative rectangle was always perpendicular to the axis of rotation. And in this case, for cylindrical shells, our representative rectangle is going to be parallel to the axis of rotation, which can be kind of confusing. So there is a method for kind of remembering this to help you. So with the disk method or the washer method, so when we're talking disk or washer, again, our rectangle is perpendicular. So the word you can remember here is, it's not really a word, if you will, but we can say it's perpendicular. So for disk method, it's perpendicular. And then for this new method, the shell method, or cylindrical shell method, we can remember, again, it's not a real word, but remember parashell. So we have a parallel representative rectangle. All right, so let's take a look at how this method works. Again, as I alluded to earlier, we have a region that we're going to rotate about an axis. In this particular figure 2.25, it's being rotated about the y-axis, which gives us a solid. But instead of thinking about it as before, we would take a horizontal representative rectangle and rotate it about the y-axis. Now we're going to take a vertical representative rectangle, like we have here in figure 2.26, part A. And if you were to take that representative rectangle and rotate it about the y-axis, we would get what we call a cylindrical shell. It kind of looks like a lampshade. And again, if we use integration, we're going to take a bunch of these, an infinite number of these rectangles. So we have a bunch of shells, one inside of another, infinite number of lampshades, if you will, all added together. But how we want to think about it is we want to take one of these shells, the way we're going to, because essentially what we need to do is we need to find the volume of one of these shells, and then through integration, add that infinite number of volumes together. And so the way we want to think about finding the volume of one of these shells is actually by cutting it vertically and then laying it out flat. And so if we do that, here on the next page, figure 2.28, we would see that if we laid that out flat, we'd actually have a really thin rectangular solid. And the thickness of this rectangular solid is going to be the dx, because remember, going back to our picture, we took a vertical representative rectangle, which has a thickness of dx, and that's going to correspond to that's our dx over here. And then the height of this is going to be determined by our function. This is our height here. And then the other dimension is actually the circumference of that shell. This is the circumference. So this is basically the circumference. If you remember the geometry formula for that, that's 2 times pi times the radius. Of course, our radius would be the distance here from the y-axis out to the representative rectangle. This would be r, this distance here, our height. Okay, so if you take that together, the volume of one of these here would be this dimension times this dimension times this dimension, all three dimensions multiplied together. So we have 2 pi r times h times dx. And then if we were to integrate it from a to b, think about it as going from a to b on the x-axis, we integrate that from a to b, that's our volume. And so that's what you see down here for the method of cylindrical shells. It's 2 times pi times r. They wrote x here because for the figure we looked at, r is the x distance. And then instead of h, they wrote f of x, or y, because h is the y, the vertical distance. Again, we can think of this as the integral from a to b of 2 pi r h dx. Okay. So let's take a look at an example. Example 1. Example 1 says, sketch the region bounded by the given curves. You should be getting used to doing this. It says, draw a representative rectangle and use the cylindrical shell method to find the volume of the solid attained by rotating the region about the specified line. So our region is bounded by y equals 2x squared minus x cubed and y equals 0. We want to rotate that about the y-axis. All right, so let's go ahead and sketch our graph. Again, make sure that you are graphing this and that you agree with the graph that I'm putting on here. This graph looks something kind of like this. Again, it's a sketch, so it's not going to be perfect. But our region okay, so here is our area, our region, and again we're going to rotate about the y-axis. And remember, this is the shell method, and we use the phrase parashell. So our representative rectangle needs to be parallel to the axis of rotation. So we're going to draw this rectangle in here, remembering that it is parallel to the axis of rotation. Our axis of rotation is the y-axis. This is parallel, so we know this is going to be a dx problem. And if we rotate that, as stated, what shape are we going to get? So we're going to get something that looks kind of like this. And it does have a thickness, but there is our cylindrical shell. And so if we think about the different dimensions of this, that's important here. So this dimension here, it's our radius, right? That's our radius. And because it's going horizontal, we're going to think of our radius as our x value. R is going to be x. And then our height is over here. It's our height. And our height is vertical, so our height is going to be y. And of course, y is determined by wherever this function is. That's the function y equals 2x squared minus x cubed. Okay? So that's the key. We can go back here now to write out our volume integral. So volume again is the integral from a to b of 2 pi rh. In this case, our representative rectangle went vertical, so we have a dx. So let's go ahead and fill in the details of this integral. So our integral is going to go from 0 to 2. The 2 pi is a constant, so let's go ahead and write that on the front. R, again, we said R was equal to x, and we want to leave it in terms of x because this is a dx integral, so we're going to have x. And then h we said was y, because that was our vertical distance, but again, we need to convert that y to be in terms of x, so y was equal to 2x squared minus x cubed. We have 2x squared minus x cubed, and dx. And that's it. Before you integrate, you do need to distribute. So we have 2 pi times the integral from 0 to 2, and distributing that x in, we have 2x cubed minus x to the 4th dx. We have 2 pi, and taking the antiderivative, we have, what's that, 1/2 x to the 4th minus 1/5 x to the 5th. Evaluate from 0 to 2. So plugging in 2, we get 8 minus 32 over 5. Plug in 0, you get 0. So doing the math here, this comes out to 16 pi over 5. 16 pi over 5 would be that total volume using the shell method. Okay, so that was an example of rotating about the y-axis. Let's now take a look at an example of rotating about the x-axis. Again, there is a formula listed here. If you like the formula better, you can. I, though, again, like to still think of this as more generic. I like to think about it as 2 pi times the radius times the height. We do know it's going to be with respect to y, and then you just fill in the details based on what your graph looks like. So it says the region for part B here of example 1 is bounded by y equals square root x plus y equals 2, and y equals 0. Well, if we're going to graph x plus y equals 2, it's probably easier to think about it in terms of what y is equal to. So y would be equal to, what's that, 2 minus x, or even negative x plus 2. So let's go again, let's go ahead and graph this region. So y equals negative x plus 2, that has a y-intercept of 2 and a slope of negative 1. This is going to be a line here. Starts at 0, 2, goes downward with a slope of 1. So it's also going to go through 1, 1, 2, 0. So here's our line. And then we have y equals square root x. It's y equals square root x. This is y equals negative x plus 2. And then y equals 0. So our curve, or our region, is that region. And it says we're rotating about the x-axis. And remember, again, the word parashell. So our representative rectangle needs to be parallel to the axis of rotation. So I'm going to go ahead and draw that in there. There is our representative rectangle. And it is parallel. And so since the thickness of this representative rectangle is now vertical, we know this is going to be a dy problem. And rotating about the x-axis, we get a shell. And so the shell is going to be something that looks kind of like this. And it has a height, because it's kind of, you think about the shell, it's kind of, we say it's more laid out horizontally, so this would be our height, if you will. Actually, let me use a different color there. It's more distinctive. Let's use blue. So this is our height. And then our radius is right there. Oops. It's our radius. And so let's think about what each of these parts are. So let's start with the radius. The radius, that's a vertical height, right? R is that vertical distance, so the radius is y. And because that we have a dy problem, we can just leave that y. Now the h, on the other hand, is going to be, the h is the distance really between the line y equals negative x plus 2, right? It's this horizontal distance, which is x, but it's not the full x because it doesn't go all the way back to 0. So it's this line minus the square root of x. Minus the square root of x. And we know things need to be in terms of y, so if you look at the line here, that's the one on the right. The line is y equals negative x plus 2, but if we solve that for x, that would be, what would that be? That would be x equals 2 minus y. So we'd have 2 minus y minus the other curve, which if we solve that for x would be x equals y squared. So we'd be subtracting y squared. So we have 2y minus, or 2 minus y minus y squared. That's our height. And so our volume, using shell method, integrate from c to d, 2 pi rh dy. So filling in the details, since we're going y, our represented rectangle starts at the bottom at 0 and goes all the way up to 1. Fill in that red area. So we'll go from 0 to 1, and then we got 2 pi, and then r is y, and h we just determined was 2 minus y squared dy. And pull the 2 pi out front, integrating from 0 to 1, distribute that y in, we get 2y minus y squared minus y cubed dy. And now we can take the antiderivative. So we get 2 pi y squared minus 1/3 y cubed minus 1/4 y to the 4th. Evaluate from 0 to 1, and we get 5 pi over 6. And so that is the second example there, or part B of example 1 for the shell method. There isn't another example 2 in this section. I'm going to post the solutions for that. So we're not going to have a video for that one. Make sure that you read those solutions in detail and ask me if you have any questions. But that is all we're going to go over in section 2.3. Have a great day.